we need to find the specific charge of this. So we've got 3 electrons, so we need 3 times by the charge in an electron, divided by the mass. The mass is 16 protons or neutrons, so that's 16 times by 1.67 times 10 to the minus 27. You don't need to worry about the electrons because they make virtually no difference to the answer, unless you're doing it something to the 4th decimal place. So 1.6 times 10 to the minus 19. We need to times that by 3, divided by 16 times by 1.67 times 10 to the minus 27. And that, we've got to remember that the charge on an electron, it's gained electrons, so it's negative there rather than positive. So it's that one there, B. Okay, what did I get the data for that from? It's there. Proton rest mass. Neutron rest mass. Right, question 9. The process of beta plus decay. We first of all need to balance lepton number. So a positron is an antiparticle, so we need a particle to cancel it. So it's got to be that one or that one. It can't be that one or that one, because they don't balance lepton number. Then we've got to balance charge at this junction here. So in this one here we have plus 2/3 coming in and minus 1/3 coming out of charge, which means then we've got 1 or 3/3 of charge coming off that way, which balances. This one doesn't balance. We've got minus 1/3 there and plus 2/3 there, which doesn't balance. You'd be making charge, positive charge there on that one. So it's got to be that one, so that balances there, which leaves us with the only choice of A. Right, a beam of wavelength lambda is incident upon a metal surface. Photoelectrons emitted. We halve the wavelength. If you halve the wavelength, you double the frequency, so you've got double the energy of each photon. So if we've got double the energy of each photon, then we're going to increase the amount of energy, the maximum kinetic energy that the photoelectrons can have. Now we need to think about this, the number of photoelectrons emitted. Well, it says that the energy is kept the same. If each photon has more energy, then that means there must be fewer photons. So that means we've got to decrease the number of photoelectrons per second, so it's C. An electron beam has a de Broglie wavelength of this, and a proton beam has the same de Broglie wavelength, and the protons have this speed. What's the speed of the electrons? Well, de Broglie wavelength is lambda over lambda equals h over mv. So those two things are constants. So we've got m1 v1 is equal to h over lambda. Those two are constant. m2 v2 equals m2 v2. So just the momenta have to be the same. So that means that we've got the mass of the proton times by the velocity of the proton divided by the mass of the electron is equal to the velocity of the electron. So we need all of those numbers, which are on your formula sheet here. So mass of a proton is there, so 1.67 times 10 to the minus 27 times by its velocity, 2.8 times 10 to the 4, and then we need to divide that by the mass of an electron, which is there, 9.11 times 10 to the minus 31, which gives us that much D. Right, this one, we've got this hydrogen atom here. We're giving the maximum energy that we're inputting is 13 electron volts. That means we can go from minus 13.6, we can go up to minus 0.6, which is in there. So we can get to this one, but we can't get to that level there. So we need to count the number of ways we can get down here, and it's 6. There's 1, 2, 3, 4, 5, and 6. So those are the 6 ways that you can get down. You could go there, 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 you could go there, then there, you could go there, then there, or you could go the whole thing in one go. So it's 6 possible ways. Or 6 wavelengths of light that will come off. Okay, question 13, we need to use V equals F lambda. So let's rearrange this and we get 1 over F, by bringing that down there, is equal to lambda over V, but 1 over F is our time period, T. So all we need to do now is plug these in. That's in centimetres and that's in centimetres, so they'll cancel if we use it all in centimetres. So we need lambda, which is 4, divided by the wave speed is 1/5. Yeah, so it's that one there. Which statement is not correct about ultrasounds and X-rays? So they're waves, so that's true. They can both be diffracted because they're waves. They can both be reflected because they're waves. They can both be polarized. Only transverse waves can be polarized. That one cannot be polarized. So that one is the false one. Stationary wave is set up on a string. This is one of these ones where we have to do a little bit of algebra first. So we get the same frequency, the same tension, the same type of material for string, but different dimensions of the string. So we're going to be using this equation here. So let's do this then. So we've got F is equal to 1 over 2L square root T over mu. So I'm going to put 1s on these for the first situation. And then that's equal to 1 over 2 lambda 2 square root of T2 over mu 2. Because they're both, the two frequencies are the same. So we can start cancelling stuff out now. Tensions are the same. That 2 is the same. So now what I'm going to do is I'm going to move all of this stuff onto the top, and I get L1 mu 1 square rooted is equal to L2 square root of mu 2. So I've just done some algebra to move all of that onto the top row. You could think of it timesing up by there and timesing that one up by there. Square everything. L1 squared mu 1 is equal to L2 squared mu 2. Right, now, mu, we're not told anything about mu, so we need to get rid of it. Mu is equal to the mass per unit length. But it's the same material, but it's going to have different mu because it's different thickness, possibly. Yes, it is going to be different thickness. All of them have got different thickness. So if we times both top and bottom by area, then that is the equation for density. So mu is equal to rho times by A. So that's the critical bit that we can then put in here. So we got L1 squared rho 1A1 is equal to L2 squared rho 2A2, and the rows are the same because it's the same material. Now A is equal to pi times by D over 2 squared, so therefore A is equal to pi over 4 D squared. Now let's put that into there, write it down here now. L1 squared pi over 4 D1 squared is equal to L2 squared pi over 4 D2 squared. You don't even need to do this step because you know that's going to cancel anyway. And then we can square root those, so we get L1 D1 is equal to L2 D2. Right, so this is L times by D. So when we multiply this by this, we've got to get L times by D. So that will give us 4LD, so that's wrong. That gives us 2LD, that's wrong. That would give us LD, so that's right. And that would give us LD over 2, so that's wrong. So it's that one. Okay, so how do you do these questions in general? You get the formula, find something that's constant, or possibly all the things that are constant, move them to one side, equate the two, and leave everything else with little 1s and 2s on, and then you want to break it down until you get something that looks a little bit like that, and then think what happens with your original values and what you have to do to your new values to make them the same. Okay. Question 16. When monochromatic light is inserted upon two slits, you get an interference pattern. One slit is then covered. What happens? So this is comparing a single slit interference pattern with a double slit. So you should know that the single slit one has a central maximum which is twice as big and goes down much more quickly than the other ones. So you don't see as many here. So the intensity of the central maximum will increase. No, it won't, because you've gone from one slit to two slits, so less light's going to get through. The width of the central maximum decreases. No, it doesn't. It doubles. Fewer maxima are observed. Definitely, you get that with double slit, so that's true. The outer maximum become wider. No, they don't. They're about the same. So it's that one there. It's diffraction grating question, so we're going to be using that equation there. D sine theta equals n lambda. We simply need to rearrange for d. D is equal to n lambda over sine theta. Right, so we've got n, which is 4, fourth order maxima, times by lambda, which is 5 times 10 to the minus 7, divided by sine of 30. So that's what d is. To find how many lines per millimetre, we need to do 1 divided by that. Now we're going to be careful here because this is all in metres, so that's lines per metre. So if we want lines per millimetre, we need to divide by 1,000, get 250, which is that one. It's dead easy to forget that. Okay. This one, we want to find which of these is in equilibrium. So for equilibrium, we need no net moment and we need no net force. So resultant force has to be equal to 0. So we need the total up and down forces to be equal to 0. So that's 10 and that's 10. So on the net forces, resultant force equals 0. That one works. That one doesn't, because that's 10 and that's 8. This one's 8 and that one, so that one does, but look, that's going to rotate that way, isn't it? So that's not going to work on the moments front. And that one's 8 and that one's 12, so that one doesn't work on the front one. So it's got to be this one. Let's just check. We've got, imagine this is not 4 newtons, but 2 newtons and a second force of 2 newtons. So that force completely cancels with that force. And then you've got these two forces and this force adding up together to make the 8 newtons, and also those two forces will equal each other out on twisting, so there'll be no couple there either. Right, which row gives the features of graphs that provide the same information? So the gradient of a displacement time, so that's ds by dt if you know your algebra. And the area under velocity time, well, that's going to be s, so that doesn't work. Area under velocity time graph is displacement. Gradient of a displacement time graph, that's ds by dt, which is equal to v again. Area under an acceleration time graph. Okay, so that's the, if you know your algebra, no, your integration, sorry, you'll know that if you integrate acceleration to time, you'll get velocity, because the derivative of velocity with respect to time is acceleration. So that is velocity. So that one works. Just check the other ones don't, because you can do this one by process of elimination even if you can't work that out. Gradient of velocity time graph, that is acceleration. Area under displacement time graph, well, that's meaningless, so that's definitely nothing. That's acceleration again. Area under an acceleration time graph, well, that can't possibly be the acceleration, so that's nonsense. So you can work that one out by saying it's not those three, but it is that one. A rocket, there's my rocket, beautiful. It's got a lift, and it's got its weight, hasn't it? So we have to, I'll just call that T for thrust. So T minus mg must equal ma, because F equals ma. Right, you've got to remember the mg on this one. This is an easy trap to fall into. People forget to put this force in, and they just work out what's the net force you need to accelerate. But that's not what we're after here. We're not after the resultant force, we're after the lift force here, which is that one. Take away that one. So that's mg minus ma. So here goes. M is, oh sorry, when you move that over there it becomes a plus. So we've got 2000 times by 9.81 plus times by 1.4 is equal to 130 kilonewtons, which is that one there. So C. Okay, question 21. This is projectile question, and there is no shortcuts here. We just got to work our way through the whole thing. So that angle there is 48 degrees. So let's do suvat, and we'll do it vertically. So we've got the distance that we travel. We want it to use this to get the time. So the distance that displacement that we travel, sorry, is 0, because we go up and then back to where we hit the ground again. So vertical displacement is 0. The initial velocity is 25 times by the cosine of that angle there, 48. The final velocity is going to be exact opposite of that, minus 25 cos 48. The acceleration, well, I've declared that as my positive direction, haven't I? Because that's what I said was positive shooting up, so that's minus 9.81, and the time is what we need to find out. So we can use it horizontally. So we're going to use the equation S equals ut plus a half a t squared. So we're going to get 0 is equal to, I can factorise by t, so I get t times by u, which is 25 cos 48, plus a half times by minus 9.81 times by t. Right, so to solve that, t must equal 0, or all of that must equal 0. So we've got 25 cos 48 minus a half times by 9.81 times by t is equal to 0. So that solution is when you fire the bullet in the first place, and this solution is when it lands over here. So let's solve that. So we get, move that over there, so we get 25 cos 48, is that, times by 2, divided by 9.81, and we get 3.4 seconds. 3.41 seconds. Right, there's no forces acting horizontally, so there's no acceleration horizontally, which means that we can just do distance is equal to velocity times by time horizontally. So that's going to be 25 cos 42 times by 3.41. So times that by cos 42, and then times it by 25, we get 63 meters, which is that one. So that's a big question, but you just got to work your way through it. Car of mass, this collides with the stationary van here. Easiest way to do these is to draw little diagrams. So that's V 580, and then it rebounds with a speed of 1.6 meters per second, and the truck, which was 1,200 kilograms, goes forward with 6.2 meters per second there, and that's 580 again. That's 0 meters per second. So we do conservation of momentum. So m1v1 is equal to m2v2. So let's do this now. So we've got 580 times by v. I'm going to take this direction as my positive, is equal to this, that plus that is nothing, yep, is equal to this one here. So that's minus 1.6 times by 580. We've got to say it's minus because it's a rebound, it's going in the opposite direction to the direction it shows as positive there. And then we've got plus 6.2 times by 1200. So let's do this. So we've got 6.2 times by 1200, take away 1.6 times by 580, and we need to divide it by this, 580, to give us V equals 11.2 meters per second, which is that one there. Question 23, this is one you should recognise. You should have done a question like this in the past. Now you're doing one in practice, so you should spot this. A velocity time graph for the balls dropped. So a velocity time graph means that the gradient will be the acceleration. So the gradient has to be constant for all the time. If this is the ball bouncing, all the time the ball's in the air, the gradient is constant. It's 9.81 meters per second squared downwards. And then just at these tiny bits here, there's a massive acceleration in the opposite direction. So it's this one. Constant acceleration, huge acceleration in the opposite direction, constant, huge, constant, huge. Now why is it this one and not this one? Because you need the velocity time graph, the area under it has to equal the displacement. So boing, like that. So that distance there is the area under that bit. That distance there is the area under that bit. That area there is the distance from there back down to there. So that area there represents the displacement from there to there. That area there represents displacement from there to there. One's positive, one's negative. So the net is always 0. Okay, so it's definitely B. Okay, right, this one's a slight trick question. Young's modulus of the second sample of wire in terms of E doesn't matter what the dimensions are because it says it's made from an identical material. Identical material means it's got the same Young's modulus. So it's that one. Right, this question here, we have 20 milliamps flowing. We've got 1.8 volts across there, which leaves us with 5 minus 1.8 is 3.2 volts across these two here. So R is equal to V over I, which is equal to 3.2 over 20 milliamps. 20 times 10 to the minus 3, which is equal to 160, I think. Yeah, 160. Right, so the resistance of all of the resistors in the circuit is 160. If that's 10 ohms, then that must be 150. The combined resistance of n identical resistors in parallel is that. Which statement correctly describes the variation of R to the n as n increases? Okay, so if we have one resistor, then we have our initial resistance of R. If we have two resistors, then 2 in parallel halves the resistance, so we go to there. So that's R over 2. If we have 4 resistors, then we go to R over 4, which is there. If we get 8 resistors, then we halve it again. So we have that. So it's decreasing and it's non-linear. So it's that one. Okay. This question here, we first of all need to think about what the resistance of so the resistance of this is R. So what's the resistance of wire Q? Well, R is equal to rho L over A, which is just a simple rearrangement of that equation there. So here we're going to times by a quarter of our value of this. This one's the same, and here we're going to divide by a half, which is the same as timesing by 2. So combine that and we get R over 2. Okay, so those are the resistances of wires P and wire Q. So we have R in parallel, oops, that's a pretty bad drawing, with R over 2. So what's the combined resistance of this? You can use the equation, but I like to think of it in this terms. To get that resistance there, I could use 2 resistors each of value R, like so, because the combined resistance of a bunch of resistors in parallel is equal to the all the same, is equal to that. So this resistor is equivalent to those 2, that one's equivalent to that one, which means that this whole network is equivalent to that, which means we've just got R divided by 1, 2, 3, R over 3 is that one. But you can just brute force it with 1 over RT equals 1 over R1 plus 1 over R2 as well. You can use that. Okay, here. What is the potential difference between here and here? Or what's the variation of potential difference between here and here? Well, first of all, we need to think about these 2 resistors here. So what's this point here going to be? Well, if this is 0 and that's 6 volts, then you can use the potential divider equation here, or you can think, well, that's 2 times as big as that, so that's going to be twice as many volts as that. So the way you divide it up, 2 to 1 would be 4 volts and 2 volts. So that's between there, 4 volts, back to there. Right, so when this thing is at this side here, you're going to, the potential difference between there and there is going to be 0. And when it's at this side here, potential difference between there and there is going to be the same as potential difference between there and there, which is 4 volts. So it can go between 0 and 4 volts, which is that one there. See. Right, this one, again, you need to use potential divider to find out the potentials at X and Y, but the ratios are dead easy. Here we've got 1 to 2, so dividing that up, then that's 4 volts, because you've got 4 volts there and 8 volts there, making you 12. And here you've got 1 to 3, so it's going to be 3 volts there, so 3 volts between there and there, and that leaves you 9 volts there, because that's 3 times as big as that one. So you get 9 to 3, that's twice as big as that one, so you get 8 to 4. So the difference between there and there is the difference between 3 and 4, which is 1 volt, which is that. Okay, circular motion question. We have a tension in the string there, we've also got the weight mg there. Now we've got to have a resultant force there, which is going to cause the acceleration, which is the centripetal acceleration. So m omega squared r, that's the centripetal acceleration, it's got to equal, so that's the centripetal acceleration, times by that makes the centripetal force. It's got to equal t, is pointing in the correct direction, and then we take away mg because that's pointing in the opposite direction. We want to find t, so t is equal to m omega squared r. So now it's just a matter of plugging in values and solving it. 120 revolutions per minute is 2 rev per second. So that's omega is equal to 2 pi times by 2. So omega equals 4 pi rad per second. 4 pi radians every second. It's going 2 revolutions a second. It's going 4 pi rad a second, isn't it? So that is going to equal the mass 0.5 times by 4 pi all squared times by the radius 0.45, and then plus the mass 0.5 times by g 9.81. Okay, that can all be solved. So 0.5 times by 4 pi squared times by 0.45, yep, plus 0.5 times by 9.81 gives us 40, which is D. Which graph shows how the kinetic energy of a simple pendulum varies with displacement from the equilibrium position? So if you think of a pendulum like so, it's got the maximum kinetic energy in the middle. So it's got to be either this one or this one, and you should know that it's a square relationship, half mv squared. You should know that it's a square relationship, so it's this one, D. You can prove it on the day if you want, but it's best to just remember that. You should know that the GPE would be that, and therefore the total would be that plus those two added together, which would be a straight line there as well. Okay, graph shows displacement of a particle performing simple harmonic motion, how it varies with time. Which statement is not correct? Okay, so the speed of the particle is maximum at t equals a quarter. So speed of the particle is the gradient, so the gradient is maximum there and there, so that's true. Potential energy of the particle is 0 at 3t over 4, which is here. Well, displacement is 0, so going back to this, potential energy is 0 there, so that's true. The acceleration of the particle is maximum at time t over 2 here. Acceleration is the it is biggest at the extremities, so the acceleration is biggest here, here and here, because it's biggest at the ends when you've got the maximum restoring force, so that's true. The restoring force acting at the particle is 0 at time t. No, we've got a maximum restoring force there, maximum acceleration, so that one's false. So that's that. And that's the end of the multi-choice section. Hope you found this useful. If you did, then please share it with your friends and your teachers. Thank you.